Hi, Bobcats. The topic of solutions here at the very end of Chapter 5 gives us an opportunity to apply what we have learned throughout most of Chapter 5 in a new situation. We've been looking at mole conversions, the concept of a mole, relationships that we can build off of the mole. And by applying those in the context of solutions, we get a chance to see how those basic tools can be used in a new setting. Our goals include correctly using the vocabulary that goes with solutions. So many of the vocabulary terms with solutions all contain SOL, solute, solvent, solution, solubility, insoluble, the list just goes on. So we want to make sure that we're clear on the subtle differences between these words, such as solute and solvent. We're going to be doing some calculations that include grams and moles. When we apply that to solutions, we're going to use the concept of molarity to describe the concentration of the solution. And we'll look at some things that are very specific to the area of solutions, and I just want you to recognize that solutions don't just have to be liquids. Most of the time when we're doing work in this chapter, we are talking about liquid solutions, but solutions don't have to be. They could also be solids or gases. So let's start with some of the basic vocabulary. First of all, what in the world is a solution? A solution is a uniform or homogeneous mixture. So we're going to take two or more things, mix them all together, and if it looks like one thing when we're all done, it's a solution. A solution is made up of a solute combined with a solvent. It's possible to have more than one solute as well. So the solute is what gets dissolved. The solvent dissolves the solute. Very often with the problems we'll work, we're assuming that the solvent is water, but it doesn't have to be. And then the solution is that combination of the solute and the solvent. When we're looking at the special case that the solvent is water, we are going to use a subscript of AQ on the substance to indicate that the solvent is water. Right, so that's what that AQ stands for, it's water. So there's a big difference between the way NaCl is written in these two cases at the bottom of the list. NaClS, well, the S stands for solid. And so NaClS is like what you get out of a salt shaker, right? It's those little solid chunks of salt. NaClAQ, on the other hand, is what you might get in a bottle of contact lens solution. Because in your contact lens solution, you have water dissolving up salt. So let's get a little practice in using this vocabulary correctly. This question asks us, how would we list the solute, solvent, and solution if we're going to make Kool-Aid from a powder? And when I say Kool-Aid, Kool-Aid means the stuff that you would drink. So when we're using that term Kool-Aid, it's what you would drink. And then the powder is what you would mix with water when you make a Kool-Aid. So let's see, the solute is what gets dissolved. The solvent is what dissolves up the solute, and then the solution is the combination of those two things. So I'm thinking the solute is going to be the powder, because the powder will get dissolved by the water. So the solvent would be water, and then the solution would be what you drink, the Kool-Aid. So it looks like the best answer here is going to be answer D. When we start to put numbers to how much solute is dissolved and how much solvent to make how much solution, the most commonly used unit of concentration is molarity. And so molarity is kind of nice because it ties in very nicely to all the mole conversions we've been doing in this chapter. The definition of molarity is the moles of the solute divided by the liters of solution. Just want to point out that denominator really is solution and not solvent. So a problem might tell us how much water was used, but what we really need to know is what the volume of the whole solution after the solute was mixed in really is. There can be some strange interactions between a solute and a solvent, so that when you mix them, the volume of the solution is less than you might expect or is greater than you might expect. We call that phenomenon volume expansion or volume contraction upon mixing. And sorry, if I start laughing, it's because my two cats are chasing each other all around everywhere, and they're just being really kind of funny right now. Okay, you might hear some background noise from that too. Okay, so when we calculate molarity, we need to put units on it, and the unit molarity can be written two ways. You can write it as moles per liter, and you'll often see that, or you can just write a capital M. Capital M and moles per liter are just two equivalent ways of expressing the unit for molarity. For our first example involving molarity, I wanted to pick something that is real and tangible, something that many people do on a daily basis, a solution that you make in real life. So what I settled on was sweetening coffee. Right? If you get a cup of coffee in the morning and you stir some sugar into it, you are making a solution. Well, the coffee by itself already is a solution, right? You've got water for your solvent, and then you've got all of those wonderful aromatic compounds from the coffee beans that dissolved up in the water when the coffee was brewed. So we already have a solution with coffee, but we're adding just one more solute if we dissolve sugar in it. So in this case, what we want to do is find the molarity of a solution made by dissolving 1 teaspoon of sugar in 8 fluid ounces of coffee. Now this problem gives you everything in the wrong units. So we're going to have to do some unit conversion along the way. And so I'm going to start by figuring out the molar mass of sugar, because we're looking for moles for the molarity calculation, but we were told how much sugar there is in terms of teaspoons. But I see peeking at that, what's in the parentheses, we're told that a teaspoon weighs 4 grams. So we should be able to go from grams to moles, but for that we need the molar mass. To add up the molar mass, we need the formula for the compound, and we're assuming that the sugar is all sucrose, which is table sugar, and that has a formula of C12H22O11. So up here at the very top of the screen, I'm going to calculate the molar mass of sucrose, and whoops, that's an 11. We have 12 atoms of carbon, and the periodic table says that each atom of carbon weighs 12 grams, or 12 atomic mass units. We have 22 hydrogens, each with a weight of 1, and then we have 11 oxygens, each with a weight of 16. All right, I'm going to grab my calculator, and let's see. So we're starting with 12 times 12, which is 144. Plus 22 times 1, which is 22, plus 11 times 16, and I'm going to let my calculator do the heavy lifting on that one. That ends up with a final answer of 342 grams, or grams per mole, for the molar mass of sucrose. All right, now our formula for molarity says that molarity is equal to the moles of solute divided by the liters of solution. Our solute in this case is sugar. Yes, there are other things already dissolved up in the coffee, but what we are considering for the molarity is just the sugar. And so in the top, we're going to have the moles of sugar, and down in the bottom, we're going to have the liters of the solution, and that solution is the sweetened coffee. Okay, So let's see how we can get there. 1 teaspoon of sugar has a mass of 4 grams. So let's see if we can get that 4 grams into moles. I'm going to switch colors just to keep these pieces of the calculation a little bit separate. So I'm going to go with green. All right, so if we have 4 grams of sugar, and we set this up to convert that to moles, I know in the bottom of the next step, I'm going to need grams of sugar. And in the top of the next step, I'm going to need moles of sugar. This is a radiation sign conversion. We're going between grams and moles. On the radiation sign, moles has the number 1, and grams has the number molar mass. Well, we found that the molar mass was 342. So if I run that through my calculator, 4 divided by 342, I end up with 0.0117 moles of sugar. Then the other piece that I'm going to need is the volume of the coffee in terms of liters. I don't have liters. Let me switch colors again here. Why don't we go with, we'll go with the orange one. What we were given about the volume, let's see, where's my pen? There we go. We were told it was 8 fluid ounces of coffee. Do this conversion up top. We've got 8 fluid ounces of coffee, and we were told as a conversion factor that for every 16.9 fluid ounces, there's half of a liter, 0.5 liters. I literally pulled that conversion factor off of the half-liter water bottle. The half-liter water bottle was also labeled as being 16.9 fluid ounces. All right, so to run this through, let's see, I've got 8 times 0.5, so 8 times a half would give me 4 up there in the top, and then I'm dividing that by 16.9. And so my calculator's telling me that works out to be 0.237 liters of coffee. All right, we now have the moles of sugar, we have the liters of coffee, so we can plug those back in to the formula for molarity. And let's see, up there in the top for moles of sugar, we'll put 0.0117. For liters of coffee, we'll plug in 0.237 liters. And so 0.0117 divided by 0.237 equals 0.0494. And the units on that can be either a capital M for molarity or moles per liter.